Welcome to this continuation lecture on deflection. As we finished during the last segment, we were focusing on an interesting method for calculations of deflection, and that is the singularity function approach. In this segment, I would like to give two examples. One for a beam that has partially uniform loading and then a few concentrated loads as well. And then the next example will be on a stepped shaft. So we see how we would design a step shaft as we will do later in the segment. So in the first example that you see here, I have a beam, and the beam has two reactions, R1 and R2. And the only loading that it has is a W load downward, which is negative, but it is only over a length of A. So I would like to write an equation for Q of X first. And as we can see here, it is going to be R1, and the R1 is concentrated. So it's a concentrated load, not a concentrated moment. So it will be x minus 0 because concentrated at 0. And since it is a load, it's a minus 1. The moment is b minus 2. And then we have R2, and this is concentrated at x minus L. So there's no issue with that. And then the issue that we want to figure out is what's happening to the uniform load. So in order for us to investigate now putting a function for the uniform load, we would see that we have to have a function, and this function should start as 0 and then goes as a step function over a distance a and then be turned off again at x equals a. So we need basically one step function that starts at 0 and then goes on forever, and then another step function that goes from here and goes forever, and then we subtract step function 2 from step function 1. So going through that, we would have to write the load is minus W because it's downward, and now it's the first step function. First step function would be x minus 0, and it's a step function. It means raised to the power 0, and then we have to turn it off. So we have to put another one with the opposite sign, which is plus W times x minus a raised to the power 0. That is the most important equation that we can discuss here. And then once we write correctly the equation for Q as a function of x, we would use the integration method to find V and to find theta, and then to find the deflection y. So let's see how this will proceed right here. So let's see that we have now, this is our expression that we derived. Now, before we proceed, it will be useful to find the reactions R1 and R2 and not leaving as unknowns. And the easiest way is just to use statics. So you have the statics, you have the sum of vertical forces equal to 0, and the sum of moments at any point is equal to 0. As we did many, many times before, we use these two conditions to find R1 and R2. So we know what they are. We can put them on the side. And for simplicity, we just leave them symbolically here. So when we have Q, we integrate it, we find V. The minus 1 becomes a 0, and then the 0 becomes a 1, and then the 0 becomes a 1, and then the minus 1 becomes 0. Very simple. No change in anything else. And then when we find the moment, we apply the same rule. 0 becomes 1, 1 becomes 2, but notice now you're using the integration rules, like integration of x becomes x squared over 2. So the integration of x to the power 1 is x squared over 2, and using the angular brackets to indicate the switching nature of these functions. So we arrived at the moment equation, and it's a moment equation. We know that m over ei is equal to the second derivative. Therefore, we can do integrate directly. However, since any angular function that starts at 0 to any power m, then we can, this is the switching occurs at x equals 0. Then we can actually use it as, let's say, x, let me be more specific, that x, let's say, to the power 1, then this is, we know that this is linear at x equals 0. If we have x raised to the power 2, then we know that this is actually x squared, and so on. Therefore, for simplicity, we throw away the angular brackets for these polynomials, but we keep them for the function that has singularity function at x equals a. So that's all what it is, and we just now proceed with the integration twice and multiply m by, we have m over ei is equal to y double prime. So this is equal to ei times y double prime. Then I integrate it once, I get a constant c1. Twice, I get a constant c2. And notice now that I can apply the boundary conditions. It turned out to be that in most cases when we at x equals 0, if we have y equals 0, then this condition gives us always c2 equals 0. And then we're only interested now in finding a constant c1. And that's basically what we will be doing on the next page here, is determining the constant c1 from the other condition that y is equal to 0 at x equals l. And that gives us c1, and we plug it back and we find now a full expression for the function y as a function of x, and that is the deflection at any point on the beam x. The only note that here that the highest polynomial is x to the power 4. So it goes from, you have term that is linear, term that is x to the power 4, but switched at x equals a. You have a fourth order term here because x times x cubed, and you have a cubic term here because you have x squared times x to give you a cubic. Therefore, we would know what the deflection is at any point. I want to just indicate here that at this point, if we look at the beam, then we will see that the beam itself is not symmetric in any way, and therefore we would have to kind of be careful in finding out what's the point where we have a maximum deflection. So if you can see here, I have a load and then it goes off, and then you have these reactions. So you cannot say that at x equals L over 2, I'll get my maximum deflection. The safest way to figure out the maximum deflection is to take the derivative of y with respect to x, where the slope is 0, and find that point x, and then you can find the maximum deflection. So it's a little bit of work to take the derivative, some algebra, and that would be a requirement that we would have. Now the next example that I would like to discuss now is a real shaft that is a step shaft. And in this example, as you will see here, the situation is that I have a shaft, and the shaft is supported on 2 bearings. So there's 2 bearings, and then the shaft is in between. Now I would like to put a pulley, or I'd like to put a gear. The way that we do it, we step the shaft from one diameter to another diameter, and stepping gives us a shoulder, and then we can actually attach the gear on that shoulder. So it would be a very good way to locate, what we call locate the gear, so we know precisely where it is. So the shaft is, as you will see here, let's use the singularity method function method to evaluate the deflections and the slopes. So in here, in this example, I have a section A to B. This is the bearing. The diameter has to be reduced to fit in the bearings, and then also from E to F, it has to be reduced so that it fits with the bearing. And then we have a section from B to C that has small diameter, and from D to E has a larger diameter. So in our modeling, since this area here, A to B, or the length is so small, and E to F is small, then for simplicity, if we just do finite element, as I'll show you later, then we would have to break the shaft into more segments. But for simplicity here, we will ignore the steps at the two ends of the shaft, where we ignore basically the step at B and the step at F, and consider that the shaft diameter is pretty much the same, and that it goes all the way to the end like this, and it goes all the way to the end like this. So it's basically, we have one size of the diameter and then another size of the diameter here in two segments for simplicity. The dimensions are shown here, and we can write now Q of X as we've learned. It will be R1 times X, and this is a concentrated force, so it will be -1. And then minus 600, and 600 is concentrated at 8, so it will be X minus 8, and this is -1. And then we have no other forces other than R2. So R2 would be concentrated at X equals L, and L is 20. So you have to the -1. In other words, the load is really simple. It doesn't have any uniform distribution, and it doesn't have concentrated moments as we would require in some cases. For example, if the shaft is connected to a gear and the gear is carrying forces on it, then the gear can create a localized moment that we would have to include. And this is moving now towards what we will do in the design, or the design example that we will work towards the end of the course. However, here would be sufficient because we're going to do the calculations by hand. So if we go further, we can write now the equation for them. We can find the reactions, R1 and R2, and it turned out to be that R1 is 360 and R2 is 240 from equilibrium, and then we can integrate Q twice to find M, and that's a result of the integration. So we have M is equal to 360x minus 600x minus 8 to the power -1. Note that I could have obtained equation 1 basically from equilibrium without having to worry about Q, because the force system is simple here. So if I represent equation 1, it will have two regions, because there is a switching function at x equals 8. So basically, below 8, I have 360x, which is this branch here. So this is m is equal to 360 times x. And when I pass by x, then this term becomes additive, so we have to add it to this term. In other words, there's one that goes like this, and then this takes away, so it goes downward, and then it has to satisfy the end condition that m is equal to 0 at the end. So between the two, we would have now this equation describes two portions of the curve. This portion here, which is straight line up to the maximum. The maximum is 2880, and then another portion of straight line all the way down to the minimum, which is 0. Note that under the exact shoulder, the moment is 2760 because it decreased a little bit from its peak. So the point that we wanted to make now is that if we are going to calculate m over ei is what counts, because m over ei is equal to y prime, double prime. So since the e is constant for this e1 is equal to e2, then we don't worry about m over ei. We can just concentrate on m over I by itself, and then noting that the e is a constant for the two segments of the beam. So if we do that, we'll find that I have m over I. If we take I for this part of the beam, which is this shaft here, I1, as our reference, and we divide everything by I1, then we find that this slope here, the straight line, will be the same as a straight line but divided by I for the 1.5 diameter shaft. Now when we go to the point, the maximum point here, and then if we now continue dividing by the same I, because we are in segment in the diameter d equals 1.5 section, then the segment AB will be parallel to the segment up here that defines the moment. It's just divided by I. However, because when we cross the shoulder at D, then the diameter increases to 1.75, and then the moment of inertia increases considerably. Therefore, the value will decrease, but we have actually a drop, immediate drop that represented by the difference between B and C. So you have a delta of m over I, and this delta is a step function in the m over I value, and the step function is dictated by the value of the larger diameter d. And then if we move now into the next section with the larger diameter, then the slope here, let me just clear this page. So the slope here for the moment is not going to be parallel to the slope for the m over I. Why? Because I here, I2, is greater than I1, and here's I1. And we did everything divided by I1. So up to this point, everything is divided by I1, 1 over I1. But from this point on, then we have to change that. We have to change the slope somehow so that we reflect the fact that I2 is greater than I1. And that's basically the math behind this part. So let's see how it works. Here is the moment of inertia for section BC is 0.2485. For section DE is 0.4604. And m over I for section B is m is 2750 at point B, exactly at point B, divided by the moment of inertia. And then m is the same at point C, because point C now is moved. We have moved to the shaft, so the shoulder is like this. We have B here and C here. So this is the drop in m over I. So the m over I at point C is 2760, is 5994.8, and therefore this distance, the difference between them, represented by this distance here, is delta m over I, and that is negative, so we drop down by a value of 5111.8. So this must be a step function in our equations as we write the equations. And then the slope of the section AB, and AB is I want to remind you that AB is really the very small section here that is showing this is AB. So the slope of AB is the same as M, but divided by I1. We're still in shaft 1, this I1. So the slope is dictated by I1. And that's what we have here, as we will see in the equation, that the slope of AB is the difference between the peak value of the moment and the value at point B. And this is the difference divided by the distance between them, which is 0.5, divided by I, which is the value of I for shaft 1. It gives us this value for the slope. However, for CD, then if I look at CD now is the long section on shaft 2, and this is CD here. So the difference would be, if I want to evaluate the slope of CD, I have to take this value, 2760, minus 0, and divide it by this distance here. And that should give me, and divided by I, the appropriate I, that gives me the slope. And that's what we did here, is the slope here is divided by 11.5. This is the distance. You get minus 521. And therefore, the change in the slope between AB and CD as a result of the increase in the moment of inertia and the second moment of area is the difference between these two comes to be 444.5. In other words, we can use the I1 as a reference and then add another ramp that is switched on at x equals 8.5, which is the location of the shoulder, to account for the increase in the slope as opposed to the section of the skinny shaft. So now if I write a general equation for m over I, the equation for m over I will have let's see if we have here, this is for shaft 1. We have this equation here for m over I, just divided by I, the same as m, but divided by I, and AB will be the same as m. In other words, we use all the way up to the shoulder. Everything should be the same as m, but divided by I. Beyond the shoulder, we have to make corrections, one for the drop, and then one for the change in the slope. And that's what we did here. So we have, this is everything up to the shoulder is the same, and then we have correction at the shoulder, and the correction for the shoulder, it gives me a drop. This is a drop by a step function, and this is the change in the slope as a result of the increase in the second moment of area. Once I can rationalize that, then m over I is the same as E times dy by dx, and d2y by dx squared, and then I integrate once, I get a constant C1, integrate twice, I get a constant C2, and again C2 is usually 0. If I have at x equals 0, the displacement is 0, and remains only C1, and I can set up an equation that y is equal to 0 at x equals 20. And that gives me the value of C1 as minus 50,565 pounds. This is 50,565 pounds per square inch with the units. And if I use the properties of steel, in which E is equal to 30 mega pounds per square inch, I have finally now the entire curve that represents the deflection of that step shaft. So that completes the problem, and I can determine the deflection at any point if I just program that in, let's say, MATLAB, and instead of taking derivatives, I can also take derivatives and find the maximum deflection by taking derivatives, or maximum slope by also taking the derivative of that curve to get theta. But an easier way is just to use a MATLAB to create an array for x, and then use this function using the properties of the step function and the ramp by defining them in MATLAB, and then you find the results of the deflection. So such calculations have been made, and the results that we have here are, you can program in MATLAB either one function, as we said, or just with if statements between 0 and 8, 8 to 8 and a half, and 8.5 to 20. That's an easier way to have like 3 equations. Or else you can just program the entire equation here, paying attention to MATLAB functions that give you the switching at x equals 8 and at x equals 8.5, as you can see in here. So having done that, we calculate the deflections, and that's an example where you can find the various values of x and various values of y, and deflection, and continues on for x and y and so forth. And then you can plot those and find the greatest deflection, and it turned out to be that it is actually at x equals 8.5. It has the greatest deflection, and reminding you that x equals 8.5 is actually really under the shoulder here, as you can see. Right here would be the maximum deflection, and not under the force. So it's just under the shoulder itself. So that's kind of an illustration of how we use the calculations using the procedure of singularity functions in computing deflections and slopes. Now, in the next lecture, we will learn a numerical method, and the numerical method is going to be based on a finite element approach. And I will just show you, it's not covered in Shigley's book, and therefore I will just upload the solution manual for that problem, and it will be good exercise for doing real design calculations for deflection of shafts using the finite element method. We're going to just kind of learn how to program in MATLAB using finite elements. What remained in the chapter is we would like to, beyond that point, learn an interesting method based on the elastic energy stored, which is based on Castagliano's theorem, and finalize the chapter looking at the buckling of shafts, where we have a significant deflection if the shaft reaches certain critical conditions.